In this video, I will give a brief introduction into Bayesian statistics. Consider the very general model shown here on the right, in which a vector of parameters gives rise to a vector of data. The goal is now to make inference about the parameter vector theta from that data. In frequentist statistics, the parameter vector theta is considered a constant, and the method of choice for inference is usually maximum likelihood, in which the parameter vector theta is identified, for which the likelihood, the probability of the data given theta, is maximized. In Bayesian statistics, however, we're treating the parameter vector theta as a random variable itself, which allows us to make inference about its distribution. The distribution of interest is the so-called posterior distribution, marked here in yellow, which is the probability distribution of the parameter vector theta given the observed data. The posterior distribution is calculated from three quantities. The first one, here in red, is the likelihood of the model. The likelihood must be specified when defining the model for any type of inference conducted. The second quantity, here in blue, is the so-called prior distribution. We're going to talk much more about the prior distribution, but in brief, it's a probability distribution summarizing or reflecting the degree of belief we have on the parameter theta before we actually visited the data. The third quantity, marked down here in green, is the so-called marginal likelihood. The marginal likelihood is nothing else but a normalizing constant in this case, as it does not depend on the parameter theta. This formula is called Bayes' theorem, or Bayes' formula, or Bayes' rule, and was introduced by Reverend Bayes back in the 18th century. Reverend Bayes also gave his name to this branch of statistics, as his theorem is so central to it. However, despite its importance, it's actually relatively easy to prove. Consider this Venn diagram here, in which this square represents the entire population of events. We then have two subpopulations. First, that with all parameter vectors theta on the left, and on the right, all those that contain parameter d. The part here in the middle is actually nothing else but the joint probability of the data d as well as the parameter theta. This joint probability can obviously be calculated in two different ways. It is either the probability of the data times the probability of theta given the data, or it is the probability of theta times the probability of the data given theta. Rearranging this equation immediately yields Bayes' theorem. So you have the probability of the theta given the data, and on the other side we have the lower equation from above divided by the probability of the data. Let's now talk a little bit about the philosophy of Bayesian statistics. The general idea is that we have some current knowledge or some belief about the parameter vector theta that is encapsulated in the prior distribution. We then challenge our view or update our knowledge by factoring in some additional data d. That comes in the form of the likelihood. If the likelihood, that is the data, is factored in with our current belief, that is the prior, we obtain the posterior distribution, which characterizes how we should think about the parameter vector theta now that we have seen some additional data. Obviously, if the data does not contain any information about the prior, that is, if the likelihood is the same for every parameter vector theta, or we say independent of theta, then the posterior distribution is just the same as the prior distribution. That is, we have not changed our current knowledge about the parameter vector theta. If the data, however, contains a lot of information about the parameter vector theta, then we are of course very willing to change our current knowledge about the parameter vector theta. In that case, the posterior distribution might look very different from the prior distribution. Bayesian statistics is often considered very close to how our brain actually works. Generally, we have some view about the world that we constantly challenge with new information and new data, and we constantly update our view of the world. But just like in real life, it is also quite dangerous in Bayesian statistics to be utterly ideologic. Consider a case in which the prior distribution rules out a particular parameter vector. That is, the prior density is 0 for a particular parameter vector. then the posterior must also be 0 at that location, regardless of how much data we have or regardless of how much information that data contains. That is, something times 0 is always 0. Before we now turn to a real example, let's first consider a little bit more about how we calculate actually the marginal likelihood, our normalizing constant. The marginal likelihood is simply calculated as the product of the likelihood times the prior, and then integrated over all parameter vectors zeta. Let us consider graphically what it actually means. Shown here on the right is the function of the product of the likelihood and the prior. The marginal likelihood is now nothing else but the area under this curve here, which is the integral of that function over the entire parameter space. Importantly, that area here is not necessarily 1, because this function is not a probability distribution. This area, that is, the integral over the product of the like and the prior, is what we actually call the marginal likelihood, so the probability of D. By dividing this function by the marginal likelihood, we now obtain a new function, this one here, that actually has an area equal 1. So it is a proper probability distribution. In fact, it is just a posterior distribution, the probability of zeta, given the data. As mentioned before, the marginal likelihood is actually a constant that does not depend on the parameter zeta. Hence, the shape of the posterior is independent of whether it's normalized or not. That is, for instance, the mode, that is, the highest point of the curve, is at the same location regardless of whether we normalize by the marginal likelihood or not. This is why we often note that the posterior distribution is actually just proportional to the likelihood and the prior. However, to actually calculate the probability density of the posterior, that is, to know the posterior probability exactly, we do need the marginal likelihood. And since it contains an integral, it is sometimes a little hard to evaluate in practice. But before we resort to these technical issues, let us illustrate Bayesian statistics using an example. As an example, consider a model in which we want to estimate the allele frequency in a population from genotyping data. The model is shown on the right as a DAG, in which we have our parameter of interest f, the allele frequency, which gives rise to genotypes that are quantified across a number of individuals, n of those exactly. We shall assume that the probability of a genotype given f is actually just given by Hardy-Weinberg proportions, that is, binomial sampling with probability f and choosing 2 alleles. The likelihood function of this model, that is, the probability of all the genotypes given f, is then simply given by the product across all individuals, and for each individual, the probability of their genotype given f calculated using the equation introduced above. Note that the binomial coefficient 2 choose gi is actually a constant that does not depend on f. We can therefore write that the likelihood function is proportional to just 2 terms, f and 1 minus f. The term f here is at the power of n1 plus 2 times n2. n1 here is the number of heterozygous genotypes, and those each contain 1 f in their probability. n2 is then the number of derived homozygous genotypes. They all come in as an f squared. Similarly, the term 1 minus f is also at the power of n1, the number of heterozygous genotypes that each contain a 1 minus f term in their probability, as well as 2 times n0, because the number of homozygous ancestral genotypes, they all have a 1 minus f squared. In order now to conduct Bayesian inference, we also have to specify a prior distribution, that is, the probability on f. We shall assume here that the probability of f is given by a beta distribution that has 2 parameters, alpha and beta. We can later see shapes of that distribution and also discuss for why that is a reasonable choice. For now, let's just look at the density function of that distribution. Notice that this density function also contains the terms f and 1 minus f at the power of something, and in front it's a normalizing constant, which is 1 over the beta function of alpha and beta. This constant does not depend on f, and we can therefore also write our prior distribution as proportional to 2 terms, f at the power of alpha minus 1 and 1 minus f at the power of beta minus 1. You already note that there is quite some similarity in the structure between the likelihood function and the prior, which will be useful when deriving the posterior distribution. The posterior distribution now is nothing else but the product of the likelihood times the prior divided by the marginal density. Up to some constants, this is therefore simply the product of this term here for the likelihood and this term here for the prior. That is, also our posterior distribution contains two terms, f and 1 minus f, and those are the power of alpha plus n1 plus 2n2 minus 1 for the case of f, as well as beta plus n1 plus 2n0 minus 1 for the case of 1 minus f. In order to now properly calculate posterior densities, we will also have to calculate the normalizing constant, that is the marginal likelihood. In this case, we are actually lucky. Looking at our posterior distribution, we realize that it is of the form of a beta distribution. Hence, the normalization constant, the marginal likelihood, must be a beta function. And we can therefore simply write that the posterior distribution is actually a beta distribution with parameters alpha plus n1 plus 2n2 and beta plus n1 plus 2n0. Here you can see an example of a posterior distribution obtained from some data simulated with a true allele frequency f equals 1/3 for n equals 20 individuals, and a prior distribution with alpha equal 2 and beta equals 6. The prior distribution shown in dashes reflects the view or the knowledge we had about the allele frequency before looking at the data. It shows that we considered allele frequency above 0.8 to be almost impossible, and the most likely allele frequencies to be a little lower than 0.2. Since the data contain information about the allele frequency, we could considerably update our knowledge or our view about that allele frequency. For instance, the most probable estimate, the peak of this distribution or mode of that distribution, is now around 2.7. That point estimate is called maximum a posteriori and is one of several point estimates that can be calculated from the posterior distribution. Apart from the MAP, a popular one is the posterior mean, because it is the point estimator with the lowest mean squared error. However, the full power of Bayesian statistics lies not in actually inferring point estimates. The posterior distribution instead gives us a full characterization of the uncertainty that is associated with our estimate. For instance, the posterior distribution tells us that it is essentially impossible to have a value larger than 0.5. It also tells us that a value below 0.1 is actually largely impossible. In fact, the probability that the true value is within any range of the posterior distribution, considered for an example between 0.2 and 0.4, is given by nothing else but the integral of the posterior distribution over this interval. So this area under the posterior here gives us nothing else but the posterior probability that the true value of f lies within 0.2 and 0.4. We can therefore easily calculate our confidence for any interval of choice. A popular way of reporting uncertainties is by providing the so-called high posterior density interval, HPD. An HPD 90, for instance, corresponds to the shortest possible interval, such that the area under the curve in that interval corresponds to exactly 90% of the posterior probability. And this interval here would then correspond to the HPD 90. Of course, both point estimates as well as confidence intervals are actually subjective because they're up to the prior. So if two people have different a priori views about the state of the world, so they have two different priors, their posteriors will also look different. As mentioned before, if the data does actually not contain any information about the parameter of interest, in fact these two people might keep their initial world view. However, the more information the data contains, the more their posteriors will converge. Let us explore that within this example. Shown here are two posterior distributions, one in red and one in blue, obtained for the same data with two different priors, also shown in red and blue with dashed lines. The simulated data in this case consisted of a single genotype, and a single genotype obviously does not have a lot of information. As a result, the two posterior distributions obtained actually match the initial prior distributions relatively closely. The largest shift from prior to posterior is obtained in the red case, in which the prior distribution is actually rather misspecified. It's a case in which the prior distribution suggests that the allele frequency must be very high. However, that seems not so compatible with the data. However, an allele frequency above, say, 0.8 cannot be ruled out from if you only observe a single genotype. Let us now look at a case in which we simulate data for 5 individuals. In this case, the data actually contains a lot of information about the allele frequency f, and consequently, the two posterior distributions look quite different from the initial prior distributions. However, the posterior distributions are still heavily influenced by the prior distributions and are thus looking quite different. There's another interesting thing to be learned from this particular example, in which the simulated data consisted basically of only homozygous ancestral genotypes. That is, N0 was 5, but N1 and N2 was both 0. This is of course most compatible with the case in which the allele frequency is 0. In this case, our maximum likelihood estimate would actually also be an f of 0. However, the posterior distributions don't only reflect the information that comes from the likelihood, but also factors in our prior information. And this is why neither of those posteriors has its MAP estimate or maximum a posteriori estimate actually at 0. But both posteriors indicate that the allele frequency is likely smaller than the priors indicated. In the blue case, the MAP estimate is actually even quite far away from the true allele frequency f star, and at f star, the posterior density is actually very close to 0. However, note, it is not exactly 0, and there is no guarantee that the true value should be close to the MAP estimate in any particular run. The posterior distribution actually reflects the total uncertainty we have about f. The low posterior density at f star actually indicates nothing else, but given the data, this seems an unlikely allele frequency. However, the posterior does not tell us that it is impossible that it's the true allele frequency. Given that the MAP estimate of the red case here is much closer to f star, we might be tempted to think that the red prior is actually a better prior. However, that would be a fallacy. Actually, the blue prior has a much higher density at the true value than the red prior. So in fact, the blue prior is more close to the reality than the red prior. But in this case, the data is so extreme that it pushes all posteriors to the left. We did a lot of simulations by always generating new data. We should actually see that on average, the blue posterior will be closer to the true value than the red posterior. That is because the blue prior has a higher density at the true value than the red prior. But let's now see what happens if we actually gonna simulate even more data. With more data, the prior is less and less important, and the two posteriors move closer and closer to each other until, if data was infinite, they would actually match. 10 individuals can hardly be called infinite data. However, we see that the posterior is already more similar than they were when we simulated only 1 or 5 individuals. And the posteriors get even closer if we simulate 20 individuals, 50 individuals, or 100 individuals, in which case the two posteriors are now very, very similar. They are both also really close to the true value, and our range of uncertainty in both cases is much smaller. It actually only ranges from, say, 0.25 to 0.45. As we have seen in the beginning, the posterior distribution is nothing else but the product of the likelihood and the prior normalized by what is called the marginal likelihood, which itself is calculated as the integral of the product of the likelihood and the prior across the entire range of the parameter. While the likelihood is given by the model, the prior is actually up for choice, and what we have seen in the example before is that that choice might actually matter quite a bit for the result. Therefore, review a few popular choices for prior distributions. One popular choice is a uniform prior, in which the prior distribution is actually proportional to 1 across the entire parameter range. In such a case, the posterior distribution becomes actually just proportional to the likelihood, as the prior does not have any extra information. This is a popular choice because the prior here reflects that we have no information about the parameter vector a priori. And in this case, our maximum a posteriori estimate, that is the peak of the posterior distribution, would actually correspond to the maximum likelihood estimator. However, this fact does not survive transformation. You may remember that the maximum likelihood estimate of a transformed parameter is just a transformation of the maximum likelihood estimate of the parameter. If we transform a parameter on which we have a uniform prior, the prior on the transformed parameter, however, will no longer be uniform. And as a result, the maximum a posteriori estimate of the transformed parameter will no longer be the maximum likelihood estimate of the transformed parameter. That's where Jeffreys prior comes in. Jeffreys prior is a function of the Fisher information. While the Fisher information is sometimes hard to calculate for many models, choosing Jeffreys prior has the benefit of actually being transformation invariant. Hence, the maximum a posteriori estimate of a parameter on which we have a Jeffreys prior will always be the same regardless of how we transform that parameter. Another popular choice are so-called conjugate priors. Conjugate priors are priors which are in the same class as the posterior distributions. In this case, the marginal likelihood can be evaluated analytically because the integral across the parameters of the product of the likelihood and the prior can actually be solved analytically. An example of the conjugate prior was the beta distribution that we chose in our previous example. Because the beta distribution is conjugate to the binomial sampling that we have, we were able to obtain a posterior distribution analytically. That is, the marginal density in this case was just a beta function, and the posterior was itself a beta distribution. But while conjugate priors are a very natural choice for mathematical reasons, they only exist for a small set of posterior distributions. And most likely, for many interesting models, there is no conjugate prior that matches, particularly not if a model contains multiple parameters. In such a case, we can pretty much choose any distribution we like, because no matter what we do, we most likely will have to evaluate this integral for the marginal likelihood anyway, numerically. On the bright side, this allows us to choose a prior distribution that actually appropriately reflects our current knowledge that we have on the parameters. Let us consider one way by which this could be done, at least in a one-dimensional case. Shown here is the function of the product of the likelihood and the prior. The goal now is to determine the area under this function that we need for normalization. And because we cannot obtain this area through analytical integration, we have to resort to a numerical scheme. An easy scheme would be to evaluate this function at a bunch of positions. This can be readily done because both the likelihood as well as the prior density can usually be calculated at any value. The area can then be obtained, for instance, using rectangle rule. While there are more elaborate schemes than rectangle rule, the accuracy of all those schemes actually depends on the number of positions at which we evaluate this function. And that means none of these approaches easily extends to high dimensions, simply because the number of positions required in high dimensions grows exponentially with dimensionality. The method of choice in these cases is then Markov-Chain Monte Carlo, or short MCMC, which we'll introduce later. Let us briefly recap what we have seen today. First, the quantity of interest in Bayesian statistics is the so-called posterior distribution, which is simply the product of the likelihood times the prior divided by the marginal likelihood. Second, the posterior distribution actually reflects the uncertainty associated with parameter theta. As a Bayesian, we are therefore not only interested in point estimates, but in actually obtaining the full distribution, which truly reflects what we currently know. Third, to calculate the posterior distribution, we need the so-called prior distribution. The prior distribution offers us the possibility to incorporate external information. That is, if we already know something about the parameter theta, then Bayesian statistics offers a very natural way of including that information. However, it also adds subjectivity. Different people might choose different priors, and they do obtain different posterior distributions. Fourth, the posterior distribution is strongly shaped by the data. If the data is very informative, then the prior choice becomes measurable. However, if the data contains very little information, then of course the posterior distribution will resemble the prior distribution. Fifth, we saw that whenever possible, we prefer to choose conjugate priors, because conjugate priors actually allow for an analytical evaluation of the posterior distribution, which is computationally very efficient. For most other priors, we then have to resort to numerical evaluation of the marginal density. That is, we have to solve the integral of the product of likelihood and prior across all parameters numerically. In low-dimensional cases, this may be done with standard tools for numerical integration. In high-dimensional cases, Bayesian statistics usually requires the use of Markov chain Monte Carlo, or MCMC,